Good afternoon. So, last time we were talking about completeness. So, the definition was that variety X is called complete if the second projection from X times Y to Y is a closed map. Hence, closed subsets of the product to closed subsets in Y for all varieties Y. Range condition, to assume something like that for all varieties. We had seen that, for instance, A1 is not complete, and I had claimed the following theorem, that projective varieties are complete. We had seen, for instance, that if we have a complete variety, if we have a morphism from the complete variety to any other variety, the image must be closed, because the image is the image of the graph, which is a closed subset of the product. So let's, however, prove this theorem. It's not completely obvious. So we have to show that for any variety, if we start with the projective variety here and take any closed subset in the product, the image is closed in Y. So we will, the main step, the main work will be to show that projective space itself is complete. So the main step, in fact, even less, main step. Main step is to show that, say, in this case, I choose the first projection from Pn times Pm closed map. Any closed. We will prove this by using the projective Nullstellensatz to reduce it to a statement in linear algebra about that the locus where the rank of a matrix variables drops is closed, because it's given by the zero set of the minors. So let's try to do this. First, we have to do some reformulations to get there. So let's state what we want. So let X be a closed subset in Pn times Pm. So then we know it's the zero set of some B homogeneous polynomials. So then we can write X as the zero set of, say, I just write like this, F1 of xy until R of xy, where now X stands for x0 to xn and Y for y0 to ym, which are where the Fi are B homogeneous in the X and so and so in the Xi and Yj. So we can assume that all these polynomials have the same degree in the Y variables. y variables. They are B homogeneous, so they are homogeneous if so they have a fixed degree in the, each of them has a fixed degree in the y variables, say d1 until dr, and we can assume that these d1 to dr are all equal. Why is that? Otherwise, so if place any fi of lower degree than the largest occurring, largest y by one such fi is replaced by several, namely something we already did, y0 to the some suitable power fi, comma, y0 to the e y 0 y, where are we, m to the I. So what does this do? So this tuple of polynomials has the same zero set as fi, because the yi have no common zeros, so which has the same zero set. We can replace any of these polynomials by a tuple of polynomials of higher degree, so that in the end all the polynomials have the same degree in the y variables, which I did choose to call d. Okay, so this was just a simple simplification. Now we have to formulate what, kind of reformulate the statement. So first, fix a point in Pn. So we want to describe what is the condition for this point P to lie in the image of X under the first projection. So obviously then P is in the first projection of X. Well, if and only if. Well, if I take the zero set, the common zero set of these polynomials, then this contains some points where the first coordinates, the x coordinates, are given by the coordinates of P. So I can write it like this: if and only if I take the zero set of f1 of P y until fr of P y, common zero set is non-empty. Definition, this is a subset of M. No, so what I mean by this is just the x variables, the coordinates, so x0 to xn are replaced by the coordinates of point P. So then it should be, so the points in x times y which lie over P, there should be some such points. So it means the zero set contains some points whose first coordinates are P. Okay, so this is the first statement. Now we want to reformulate this with the projective Nullstellensatz. So by the projective Nullstellensatz, You know that the zero set of some polynomials in, so if I fix here the coordinates of P, these are now polynomials in Y. So the common zero sets of some polynomials in Y is empty if the ideal generated by them contains all monomials of degree S for some S. So, and then also for all bigger ones. So we know. Anyway, the projective notion that's said what I just said. So that means that this is equivalent if and only if. If I look at the ideal, maybe I write it here, if I look at the ideal generated by these, F1 of Py R of Py, this does not contain all monomials of degree S. So if this holds for all S bigger than 0, because the statement was the common zero set is empty if there exists an S bigger than 0 such that it contains all monomials of degree S. So this is equivalent. So this condition I call star S. So by our definition, star S is trivial for S smaller than D, because in degree smaller than D, there's actually no polynomial. These polynomials have all degree bigger equal to D. So this corresponding, the ideal generated by this part in degree S, I mean the part in degree S in this ideal is just consists of 0. So this is trivial for S more equal to D. So that's enough to show. So what we have to show is so the following condition, which I call double star. So for all S bigger equal to D, the set of all points P and Pn such that P satisfies the condition star S, okay, is closed in Pn. Why is that enough to show that? Then, by what is written here, we see that P1 of X, so the image of the points in X, is by what I just said, just equal to the intersection over all S bigger equal to D of this set. So if each of them is closed, then this intersection is closed. No, because the points, so P lies in P1 of X if and only this does not contain all monomials of degree S for all S. So it means if it lies in the image of this. Okay, and now we want to check this condition, double star, that for all S bigger equal to D, the set of all points in Pn such that P satisfies this condition does not contain all monomials of degree S is closed in Pn. Okay, now we have to, you want to translate this into some linear algebra. So we fix some S bigger than D. We have to show the statement. So we denote monomials y of degree s just by, say, mi of y. Y means again y0 to ym, mi of y, where knows that the number of them, the dimension of the vector space of polynomials of degree s in m+1 variables is, one can easily compute that this is m plus s. Choose m. Okay, so these are the monomials. Like this, I have as many of them. Let's also name the monomials of degree s minus d. So denote the monomials y. Just write again in just for once y0 to ym of degree e by m, so ni of y, well, obviously now the number is m minus d plus a. Okay. So what are the elements of degree d in this, of degree s in this ideal? So homogeneous elements of degree s. Elements homogeneous of degree s in this ideal are those? Well, it's just all combinations. So are the linear span, so all linear combinations with coefficients in our field K of the ni of y fj of py. How do you get a polynomial in y which is homogeneous of degree s? You take a polynomial of degree s, homogeneous polynomial of degree s minus d, so any linear combination of monomials, and you multiply it by this polynomial of degree y, and the elements who lie in this ideal of this degree are just all combinations like this of our given elements in the ideal of our given generators. So again, just to say, I from 1 to K from 1 to R. So, okay, now I want to write down these things again, but now instead of p, I take the variable x, and I just write down all of them in any order. So denote the ni of y, fj of xy by, I say, so all of them that we get, gk of xy, k equal 1, some number t, as many. I mean, if you wish, you could take t to be this times r, okay, in any order. So these elements here, the linear span of these elements, if we replace x by p, is precisely the elements of degree s in y in this ideal. So therefore, the condition star s is equivalent to the linear span of, if I take these gk's as before, but now I put p instead of x, 1 smaller equal to k smaller equal to t, is not the whole of all monomials of degree d in y. So it has dimension smaller than, strictly smaller than m plus s. Choose s. Okay, so we have a statement. So you can see the linear span of something is supposed to have dimension smaller than something, so you can see it might have to do with the matrix not having the full rank. And so let me write this out. So we can write k of xy as sum I equals 1 to m plus, room, sum I equals 1 to m plus s choose s of somehow a I k of x times mi of y. But the mi are these here. We know that, we just, each term I can pick out, I can sum. So this thing is a bihomogeneous polynomial in x and y, whose degree in the y variable is s. So it will be each. If I just collect the if I just put together all the monomials of degree s, then I can write it as a sum like this, where this is a polynomial in the x variable. So with a I k of x, where x again stands for x0 to xn, a homogeneous is a polynomial in k x0 homogeneous some degree. So the dimension of the linear span themselves are of the linear span of these vectors the dimension of this is equal to the rank of this matrix, because these are bases of this vector space of dimension m plus s choose s, and I take linear combinations of them, then the rank of the linear span of these elements is equal to the rank of this matrix. So the dimension is equal to the rank of, take this matrix AIK, I replace the x variables again by p, I from 1 to m plus s choose s, and k from 1 to t. So that means now, what does it mean? So the locus, so the set, where the condition, where this thing has rank smaller than m plus s choose s, consists of all the points p and pn, where the rank of this matrix is less than m plus s choose s. So thus, the set of all points p and pn such that this condition star s holds for p is equal to the zero set of all m plus s choose s times m plus s choose s minus of this matrix where I put again x for the variable. Now, this is, if I take the, so these all ai k of x are homogeneous polynomials in the xi, so the minus are the determinants of the sub matrices of this dimensions. So these are all homogeneous polynomials. In x0 to xn. So that means the set of all points which satisfies this condition star s is a zero set of these homogeneous polynomials that thus it is closed. So thus set of all p and pn that star s holds for p. Closed. We had seen from this that the image P1 of x is we had seen here. In fact, it's just the intersection over all s bigger equal to d of this locus. Okay, so this was the main step. It's a bit, I mean, not extremely difficult, but a little bit complicated to keep track of it. But it's a nice trick to reduce this problem, which is in the beginning not at all clear what one is supposed to do, to reduce it to this simple statement of linear algebra about the rank of matrices. Okay, so now the rest of the proof is quite simple. So now we have shown that the second projection, or the first projection from Pn times Pm to Pn is closed. So now second step, we want to show that Pn itself is complete. So now, therefore, we have to take any, instead of taking the projection, having the other factor to be also projective space, we have to take any variety. So let y be a variety. So we can assume y is quasi-projective. Because by our definition, it's, I mean, either quasi-affine or quasi-projective, and quasi-affine varieties are also quasi-projective via the embedding of affine space into projective space. So, I mean, maybe by our definition, every variety is quasi-projective, but we can assume it lies in some Pm. So let's take closed subset Z in Pn times Y. Now we have to show the second projection of it of Z is closed in Y. So let's take the closure of this in Pn times Pm. So let Z bar closure of Z. Then its second projection will be closed in Pm by the first step we did. Then P2 Z bar is closed M by the first step. But what's the relation between Z and Z bar? The claim is that by definition, Z is just the intersection, this is the closure of that, then Z is equal to Y intersected Z bar. No, that's always the case. So what is P2 of Z? So now this is, I said it wrong, obviously. This was closed in this product. So this is Z is equal to Z bar intersected with N times Y. No? Because that's, you have the Z is a closed subset in Y, so it's the intersection of its closure with the set. So therefore, P2 of Z is the second projection of this. Y. But what, if I take a set and I project from Pn, so from the whole one Pn times Y to, so here I have the whole of the first factor, and here I have the Y. So this just means it's the image of P2 of Z bar intersected Y. No, because I just Z bar, I intersect with the whole image of Y, so this is this. But this, by definition, it's the intersection of a closed subset of Pm with Y, so it's closed in Y. Okay, so this shows that Pn is complete. And now we want to show that any projective variety is complete. So let X in Pn be a projective variety. So let Z in, and let X be any variety, Y be a variety, and let Z be a closed subset in X times Y. Then, as X is closed in Pn, Z is also closed in Pn times Y. know, if you have something closed in something closed, it's closed also in the other one. And so we can just apply the 2 to the second part, so that's by 2. 2 of z is closed in Y. Okay, so you can see these steps were relatively formal, whereas there we had to work a little bit to reformulate it. So this shows that X is complete. Any projective variety is complete. Okay, so this was this statement. Are there any questions? So I remind you that we had deduced from that that the image of any morphism last time we had this corollary that phi from x to y the morphism varieties with x projective then image closed. This is done by applying this theorem to the graph of this morphism. So I wanted to just give one example. So in particular, it gives us a way, so this allows construct many projective varieties. Now we don't have to necessarily give polynomials of which it is the zero set. We can just take any variety, we apply a morphism to it, to some projective space. If we start with a projective variety, we take a morphism to another projective space, the image will always be a projective variety. So x to y to Pn is a morphism X is a projective variety. Then phi of x so x, so we know that phi of x is closed in Pn by this result. And it's also irreducible because we always know if you have a morphism starting from something irreducible, the image always has to be irreducible. It was essentially an exercise, but it's very simple. And so even if we have no idea what the equations are of which this phi of x might be the zero set, we always know it's a zero set of some set of homogeneous polynomials. So one example, to give it was one slightly non-trivial example, which is the Veronese embedding. So let's say we choose that n and d some positive numbers. We write n to be this binomial coefficient. So then we can define a morphism from Pn small n to P large N. So denote I, m I of y0 to n, all the monomials of degree for I from n, all monomials in the y variables of degree d. You can easily check that the number of these monomials is n plus d choose d. So that if I number them like this, it works like this. So then the Veronese embedding just the map given by all these monomials. So is, I call it nu d from Pn to n, which is just given, maybe I write it here, it's just given by all these monomials, m0, mn. So I apply all the monomials to the variables here. So I send a point P and Pn to the application of all the monomials to these things. So you can see this is, so it's given by polynomials, homogeneous all of the same degree, namely d. And to be a morphism, I need that these have no common zero sets, but this is easy to see. So this is a morphism. Because among the Mi, we have in particular the monomials y0 to the d until yn to the d. There are y0 to the d and so on until yn to the d. And these have no common zeros, because if y0 to the d until yn to the d are all 0, it means y0 to yn are all 0, but that's not a point in projective space, which have no common zeros. So this is given by a tuple of polynomials, homogeneous all of the same degree with no common zeros, and so it's a morphism. It's a polynomial map. So this is a morphism. The image Vd n is called the Veronese variety. This occurs sometimes as an example for some property, or as a counterexample. In particular, we have so it's an important example of a variety, and I claim that this map is actually an isomorphism. So this thing is just Pn, but it's interested. It is embedded in this larger Pn in an interesting way. So this I just do claim as an exercise. You can find the inverse morphism. So nu d from Pn to the image. It's an isomorphism. And so So the simplest example of this is if, well, obviously if d is equal to 1, this is just the identity from Pn to itself, so that's not so exciting. But if instead n is equal to 1, we have this rational normal curve, which I already had mentioned. It is a special case of this. So simplest example. So this map nu d from P1 to so what is the map? It's given by all monomials of degree d in the variables on P1. So it just means it sends a point AB to, to a to the d minus 1b and this is called the rational. This we already had is the rational normal curve. Okay, so that was much as I wanted to say about this. So now I want to briefly talk about rational maps. So, so here this ends the story about products, and now I want to briefly talk about rational maps. So one of the problems of algebraic geometry is that somehow there's not so many morphisms. So you use morphisms to compare things, and the relation between things. So there are not so many because morphisms are defined in terms of mostly, I mean, for instance, for affine varieties in terms of regular functions, or the definition for projective varieties was also a bit complicated. So one wants, so on the other hand, so one wants maybe something slightly less than a morphism, which is a morphism which is not defined everywhere. So, and this is not, so in fact, a rational map between, so let me just say that X and Y be varieties. So a rational map often denoted by phi from X and then with a broken arrow Y to Y is a morphism from U to Y for an open dense subset of X. Non-empty open subset. And you know, as we know that the open sets in varieties are very big, it actually contains the fact that there is a rational map from X to Y, or the rational map from X to Y itself will give us a lot of information because it tells us what happens on, almost everywhere on X, except for some very small subset. So it's a slightly, okay, so Now let me give a precise definition of that because it's ever so slightly different. So first we have the following lemma, which we want to use. So if we have, let's assume that we have two morphisms between the same algebraic varieties. Let phi x to y be morphisms of varieties. So if they are equal on a non-empty open subset of X, they are equal. If phi restricted to U is equal to psi for a non-empty open subset of X, then quite different from differential geometry. So it's all very rigid. If I know what the morphism does on an open subset, I know what it does everywhere. And this, in some sense, we already proved because it follows from what we did with the separatedness. So by a previous result, we have, if we look at the set Z, which is the set of all points in X, such that phi of p is equal to psi of p, we had seen that this is closed in X, because it's the inverse image of the diagonal in something under a suitable map. That's how we proved it. So it's closed in X. And so according to this thing, if it contains an open subset, then it's the whole of X. So it contains a non-empty open subset. U in X, so Z is equal to X. Okay, so therefore we can define a rational map slightly differently. We can say it's an equivalence class of maps defined on open subsets. Or, as we shall see in a moment, we can also say it's a map defined on a maximal open subset. So let's see definition. Rational map F from X to Y of varieties is an equivalence class put it in brackets U of pairs U subset X non-empty open subset and a morphism phi from U to Y. What's the equivalence relation? Yeah, I should maybe say morphism of pairs. Equivalence class of pairs U, phi, where we have this. So with the equivalence relation here, U equivalent to V psi, if, by definition, if and only if, so these are both open subsets, X is irreducible, so these things have to intersect. So if we take phi restricted to the intersection U intersected V, this is equal to psi restricted to U intersected. So it's an exercise. Check an equivalence relation. So the symmetry and the fact that every element is equivalent to itself is essentially trivial by definition. The only thing which is not complete, not obvious a priori, is the transitivity, and that follows quite easily from this lemma. Okay. So you can also describe it in a different way. Maybe that would feel better than talking about equivalence classes of maps. You just can say we extend this rational map to the biggest open set on which it can be defined. And that is the rational map is the map like that. But in some sense, the more natural definition is this. But so you can just say, so for a rational map, from X to Y, the domain is just the following, is the domain of phi, take it's the union over all V psi which are equivalent of the set on which it was defined. So this is obviously an open subset of X, and we can define phi on this domain by just applying the corresponding map here. So we define, so then we have morphism phi from the domain of phi. So Y, by sending, by putting phi of P equal to psi of P whenever our U is equivalent to V psi and P lies in V. And again, it's easy to check that this is well defined. There might obviously be many such open subsets in which P lies, but by the statements that we have here, the definition of the equivalence relation, it follows that this is well defined. So it's an open, and that somehow clearly seems to be the maximal open subset on which this map is defined. If the domain of phi actually happens to be the whole of X, phi is a morphism. So we say P is defined at P if P lies in the domain of phi. So this is all rather similar to what we did with rational functions, and so it doesn't come as a surprise that rational functions are a special case of rational maps. So remark rational functions the rational, we can write better, f in kx are the same as the rational maps from X to A1. And if I look at the rational maps to an, they are just given by n tuples of rational functions. So let X be a variety. And we take some let F1 to n the rational functions on X, then I just take F1 to Fn X to An, the rational map. And in fact, it will be defined on the intersection of the domains of these rational maps on section I equals 1 to n of Fi. Of course, if I have a point which lies in the domain of all of them, P, then I can just send P to F1 of P until Fn of P, which lies in An. But where one of these functions is not defined, I don't know where to send it to. And similar for maps to projective space, we saw that maps to projective space are given by tuples, equivalence class of tuples of rational functions. But it was a little bit complicated. You know, they must find a representative so that for every given point, we must find a representative so that all of them are defined there and not all of them are zero. And that's actually difficult to achieve. So it's easier if one just wants a rational map. Namely, we can just take a tuple of rational functions. So let X n be a quasi-projective variety. Actually, I don't need, whatever. I don't need to let X be a quasi-projective variety. Let F0 to Fm some elements in Kx, any elements, not all zero. So not all of them should be the zero map. one of them must be somewhere non-zero. Then, if I just put f0 m, which sends from x to n pm, which sends a point p to f0 of p, m of p. That means we take the homogeneous coordinates, we choose homogeneous coordinates for this point, we put the same homogeneous coordinates into all of these. This is a rational map. Because there will be a non-zero, there will be non-empty open subset of X where not all of them vanish, because at least one of them is not the zero function, so the function where it's not zero is an open subset. And there's also an open subset where all of them are defined. And so in the intersection of these two open subsets, at least, this will be a morphism, and so it's a rational map. Okay. So these are these examples. So you can in particular see it's extremely easy to give rational maps, whereas with morphism it's a bit more difficult. Write down anything which makes sense, and it is a rational map. The morphism, you have to check things, and for instance, you don't have any morphisms for Pn to An, if n is bigger than 0. Whereas here, rational maps, there certainly are many. So now, obviously, if you have morphisms, you want to compose them, so you also would like to compose rational maps. But that's not completely obvious that this should always work, because you can imagine that you have two maps, phi and psi, and the image of phi might not intersect the domain of psi. So then you cannot possibly compose them. So to fix that, you want to look at so-called dominant rational maps, that is, rational maps whose image is dense. So would like compose rational maps so we have phi from x, y, and psi from y to z, but this might not be possible. Because it could be that, say, phi of the domain of x, which I could call the image of phi, intersected the domain of psi, is empty. So then I cannot possibly compose them, because there's no, I start with a point here, I send it somewhere where this thing is not defined, so there's no way to compose them. So to remedy this, we restrict our attention to dominant rational maps, which are rational maps whose image is dense. So definition. The rational map x to y is dominant if phi y. Note that we can always make a rational map dominant. If phi of x is not dense in y, replace y by the closure of phi of x in y. So then we have a dominant rational map from x to the closure of phi of x in y. Always x to closure is dominant. So if we're willing to do this, every rational map can be considered to be dominant. So now we want to compose. So we can compose rational maps if the first one of them is dominant. So let from x to y be a dominant rational map. And psi from y to z, just a rational map. Then I can compose them. So I can take, we put, say, v to be the domain of phi, is defined, intersected the inverse image under phi of the domain of psi, or if you want, this is an open subset of X, and it's non-empty because this is an open subset, this is an open subset. So phi to the image of phi is open, and so this is open. Anyway, this is an open subset of X, non-empty in X. And so we can define, we can take V and psi composed with phi as a representative of the composition. One should note that the composition might be defined on a much bigger set. It might even be that you have two rational maps and their composition is a morphism. Because morphism just means that if I extend it to the biggest open set on which it is defined, then this is the whole. So in particular, we can talk about isomorphisms if birational isomorphism or birational map is a dominant rational map which has an inverse. But maybe first I can talk about the pullback by a dominant rational map. Fine. Pullback. Dominant rational map. So if phi from x to y is a dominant rational map, f is a rational function y, then I can compose them. I mean, a rational function is just a rational map to A1, so I can compose them in the same way. So then phi star f is equal to the representative of the composition, which I still just want to denote as C composed with phi. So this is just F composed with phi, which is a rational map on X. So, we just apply the same scheme as here. Take the domain of phi intersected with the inverse image of the domain of F. On this, it will be defined and will be given by rational function. So clearly, we can see that if we take the sum of two rational functions, it gets mapped to the sum. If we take the product of two rational functions, it gets mapped to the product. So it turns out that this is a K-algebra homomorphism. So the map phi star from Ky, the rational functions on y, to the rational functions on x, is a K-algebra homomorphism. And obviously, it's compatible with composition. And if I take pullback by the composition, this is the composition of the pullbacks the other way around. No, that follows directly from the definition. Now, I want to look at this particular case of dominant rational maps, which are the birational maps. So these are maps which have rational maps which have an inverse. And if such a thing exists, it means that the two varieties contain open subsets which are isomorphic. So definition. Dominant rational map X, Y, called a birational map if there exists an inverse. So if there exists a dominant rational map which I just call phi to the -1 from y x, such that the composition is the identity in both directions. So such that phi to the -1 composed with phi is equal to the identity on x, and composed with phi to the -1 is equal to the identity on y. So just to be sure you understand, these maps are defined on some open subset. They don't have to be defined everywhere. But so this identity, and so in particular, a priori, if I just take this representative of the composition, this will not be the whole of X. Still, as a rational map, this composition is supposed to be equal to the identity on X, which is the same as saying, by the definition of what it means to be equal for rational maps, that there's an open subset of X on which this composition is equal to the identity. Then, as a rational map, this composition is the identity. That was our definition. And the same the other way around. So in this case, if such a thing exists, we say that x and y are birational. And write normally maybe x is birational to y. So for isomorphic, we did it like this, and for birational, we do like this. It's a slightly weaker equivalence relation. Now, as a last thing, I want to see that you can describe this birational in a different way. So two varieties are birational if and only if they contain open subsets, one in x and one in y, which are isomorphic. And also if and only if the fields of rational function on kx and ky are isomorphic as k algebras. That the information contained in this is precisely what this field is. Maybe, let me see. So first I have this theorem that x and y varieties then x is birational to y if and only if kx isomorphic to ky as k algebras. Will not maybe give a complete proof. I just prove the easy direction, I think. The other I can leave as an exercise. It is not so different from what we did a long time ago for affine varieties that morphisms between affine varieties correspond to homomorphisms between the coordinate rings. And so one can reduce this to this, but I just give the easy direction. So only show one direction. Exercise. So if I take, so this is really simple. So let phi x to y be a birational map. Then pullback star. So birational map, and so I can also take the inverse. So with inverse one. So then obviously we have, by what I said, phi to the minus 1 composed with phi is the identity on x. So thus it follows that if I take the pullback by the composition of the pullback is the pullback by this. So phi to the minus 1 star composed, phi star, so it goes the other round, phi star composed with phi to the minus 1 star is equal to the identity on x star, which is equal to the identity on x. And so that means that, and in the same way the other round, obviously, that phi minus 1 star composed with phi star is equal to the identity, right? And these are homomorphisms of K algebras, so thus star from kx, ky is a k-algebra homomorphism. Isomorphism. Now, to do the other direction, you would have to see, you can reduce to the case that x and y are affine varieties, and then it's given by, this map would be, the phi would be given by an n-tuple of rational functions, and then there's some open subset on which they are defined, so they give, anyway, so let me say it again. We can assume by replacing x and y by open subsets that x and y lie in affine spaces. Then we can look at what, if we are given a k-algebra homomorphism, we look what it does to the coordinate functions, and then these coordinate functions give us rational map from x to y. This is very similar as it was in the affine case for the morphisms. If you just look back to what we did then, it's basically the same proof. So let me see if there's anything more I can say. Well, and corollary. Or anyway, it's not really corollary, but anyway, so let x and y be varieties. So it's equivalent x first, x and y are birational. And they contain isomorphic open subsets. There are non-empty open subsets u in x and v in y, which are isomorphic. Well, this actually, it doesn't follow from that, it follows directly from the definitions. So, slightly more difficult one is this, but it's almost direct. So let assume they are birational. So let phi from x to y be a birational map. And psi, the inverse, is psi from y x inverse, rational map. So if I take phi, and I take it as a map from the domain of phi, intersected the inverse image with the domain of psi. Still an open subset, then this will map this thing to the domain of psi, intersected the inverse image under psi of the domain of phi. Because where these maps, where phi and psi actually are both defined, phi is the inverse of psi. So if I take this thing and I apply phi to it, then it sends e to the -1 of the domain of psi, the domain of psi, because phi just does this, and it sends the domain of phi to phi of the domain of phi, which is to phi of the domain of phi, but phi is psi to the minus 1, where they are defined. So this is just this. So it's a morphism sends this to this, and the inverse of the map is just psi. From the domain of psi, projected psi to the minus 1 of the domain of phi. So, domain of phi. Intersected phi to the minus 1, the domain of psi. The fact that I've written it down in such a symmetric way makes it evident that this is mapped to this, and the inverse map just maps it the other round. And so, thus, phi is an isomorphism. Phi thus phi, so is isomorphism. Open subsets. Okay, so I find that if x and y are birational, then there are non-empty open subsets which are isomorphic. And conversely, is more obvious. If U is open in X, then obviously the identity map from U to X is a birational map, because it's in this case, it's a morphism from U to X, and its inverse is the identity from X to U. It's defined on the open subset U. So if U subset X is open, then U is birational X. So thus, if we have this assumption that we have open subsets which are isomorphic, so thus, under our assumption, we have that X is birational to U, which is isomorphic to V, which is birational to Y. And so we have a composition of isomorphisms and birational maps, so this is a birational map. Okay, so that's that. So maybe I will stop here. Next time I give a couple of examples, but maybe it will be good to review this. So if something is not, so it's maybe, I don't know whether it's a bit abstract, but that's, it's still, I don't go very much into this. I just wanted to mention this because it plays birational geometry plays an important role in algebraic geometry, even if we don't do much with it. And so at least you should have seen it. Okay. So, are there any questions now? If not, we see each other on Friday, so I'm sorry that I had to cancel on Monday. There was some important thing I suddenly had to do and I had to leave. But on Friday then at 2 o'clock we will have the next lecture. Okay, I wish you a good evening.
Thank you.
Thank you.
Thank you.